Alright, so we are going to be doing two things in this lesson. Mainly because transformations you guys have already done. Okay, it isn't anything new. We've done transformations multiple times with you guys. I'm just applying it to a different function. Okay? So that shouldn't take us too long. Just take me a moment to review it with you for a few minutes there. And then, of course, graphing the radicals, that's going to be the heart of the lesson. That's the new stuff. Okay? Alright, so first things first. Let's show you what the parent function is, which you guys already know what it is, right? The parent function of a radical is the square root of x, right? Alright, so that's the parent function. So what you guys are going to be doing is telling me what happens when I put a value in front of it. Or what happens if I put a plus or a minus number on the outside. And you guys have seen these letters before, to where we have told you that A does a certain thing. And we've told you that x minus h plus k, remember those? You guys have seen this a lot. Now, the difference is that when we started off, we taught you with squaring functions, right? The quadratic functions. Then I showed you how to do it with polynomials, where your exponent changed depending on the highest degree, right? You guys remember that? Mm-hmm. All right, so all that's different now is that I have a radical. But all of the descriptions, all the transformations don't change, okay? Anybody remember what A does? Okay, it's our dilation, right? And our dilation point is a vertical stretch or shrink. Or, I heard somebody say the R word. Reflection. It's also the reflection, okay? So I usually tell you guys, hey, if A ends up being negative, so we say if A is less than 0, then it's a reflection, right? And it's a reflection over the x-axis. And then we broke it down even more. I said, hey, if your A ends up being a fraction, then we call it a vertical shrink. Okay, and that's our dilation point. So I know in a lot of texts now, they're not saying vertical stretch or shrink. They're saying that it dilates to a certain number. So that's why I put that in your goal. I am fine with vertical stretch or shrink, but I want to make sure that for the SATs, if they use dilation, you go, oh, that's my A value. I got you. All right, and then, of course, if it's greater than 1, if it's not a fraction, we would say that it's a vertical stretch. Kind of coming back to you? Easy enough? Okay. Anybody remember what H does? Yeah, it's a horizontal shift. And remember, you got to be careful of this minus sign. Okay? So if H is greater than 0, then it shifts to the right. So we say horizontal shift right. And if it's less than 0, it's a horizontal shift left. Now, a lot of students won't use this as their basis. Because if I have something to where it's like this, see, x minus 3 versus x plus 3, the minus 3 is actually your shift to the right. And your plus 3 is actually your shift to the left. And that's because of the minus sign we had up here. Does that make sense? So I put an example next to the correct direction just so that you knew which is which. Okay? So on this one, your h is actually 3, and on this one, your h is actually a negative 3. Just be mindful of that. All right, what about our k? Yeah, that's our vertical shift up or down. Now, since k has a plus sign, there's nothing tricky about it. Okay, if k is positive, it goes up. If k is negative, it goes down. Plain and simple. It only gets backwards when it's under the radical or in parentheses being squared. That's the only time when it starts working backwards. And by the way, you guys, that is always true. Even for next year, when we get into trig functions, these are exactly the same. They don't change. And so you guys will see this again next year, just with a different function. So we've seen this a lot now, right? You guys should all be experts on this. I think you just had a test over this too. I think I had drop-down boxes for you guys on the online test, right? And you guys had to like pick whichever one with whichever letter. Now, there is one other thing that I'm going to mention, and it's not that you won't be tested over it. It's just sometimes it pops up in a random problem, and I'll forget about it. So I always try to mention it somewhere, okay? But I don't think you have any homework problems where it's a negative, okay? And what it is this value right here in front of that x. So if it's a negative, it's still a reflection, just like your a. But instead of reflecting over the x-axis, it reflects over the y-axis. Okay? And that's because it's affecting our horizontal values instead of our y values, our output values. Okay? So I'm going to put this on here just so that you can be introduced to it. So if your b ends up being negative, we call this a reflection over the y-axis. And now this is why I don't like using that term of dilate, is because with A, we know that A is a vertical stretch or shrink, right? So B isn't a vertical stretch or shrink, it's a horizontal stretch or shrink. So it's a little bit more difficult for you guys to see the horizontal stretch and shrink here on these type of functions. But when we get to our graphing functions next year for sine and cosine, you guys will be able to see it. Okay, here's a little preview into next year, by the way. Don't sketch this. Sine and cosine functions look like so. They look like a slinky. You guys know what a slinky is? Okay, so you guys will actually be able to visually see the horizontal stretch and shrink happening. Because it will either look like this or it will look like this, where it's really, really, really tiny, okay? But with these graphs, we don't really talk about it because you can't really visually see that horizontal stretch and shrink happening. Does that make sense? But I do want to point it out now so that when I do actually teach it to you guys, it won't be a brand new concept. It will be, oh, this is the second time I'm seeing it, so you'll understand it a little bit better, okay? All right, so it works out the same as our A value. It's the exact same, except for these will end up being B's, and this will end up being a horizontal. Okay? Remember how I said that if it's under the radical or in the parentheses, it works backwards? Remember how I said that? Yeah. So, just like our H, where it kind of goes backwards because of that minus sign, right? Same idea here. If it's a fraction, it ends up being a stretch, and if it's not a fraction, it ends up being that shrink. And that will make more sense to you next year. I can even actually give you guys a great visual. We actually will all run around the room. It's really fun. It's actually a really funny demonstration. Okay? Actually, I can kind of describe it to you. You guys know the track down there, right? Okay. So, if we all started running at the same time, okay, and let's say, since I'm a little bit older and tired, that I'm running half as slow. So is it going to take me more time or less time to get there? More time, right? But I'm half as slow, so that means that my B value is 1/2. Right? So that's why it's a horizontal stretch, because it's taking me longer to run around that track. Or if you want to say half as fast, I guess you could say. Does that help? Half as fast. All right, what if somebody is really, really good? It's a track star, okay? And they're running twice as fast. Would they get there faster? Yeah. So they shrunk down their time, right? That's why it's a horizontal shrink. See how that works? So, there's your preview into next year. Okay. All right, questions on transformations? Shouldn't be. You guys have seen this. Do I need to do an example for you? I think you guys are good. Okay, I'll do one quick example. Alright, here you go. Alright, I recommend that you work left to right. That way you don't forget any numbers. So, start on the left. Reflection, that's the negative sign. Next.
Horizontal shift left.
You forgot about the 3.
Oh,
vertical stretch, right?
Yeah.
Alright, what were you saying about the 5?
Horizontal shift left.
And what about the 1?
Vertical shift down.
There you go.
I have a question.
Sure.
How is it vertical?
Because the 3 is bigger, so you're pulling on it. Think of a rubber band. When you're putting a bigger force on it, you're stretching it, right? That's why the 3 is stretching it.
So we don't look at the negative?
No, because it's two separate things. This is a single value, and then this is a value. Okay.
Boy.
Alright, example 2. Graph. Alright, so the first point should be fairly easy for you guys to find, okay? And that's because the first point is just your horizontal and vertical shifts. So what's our horizontal shift here? Alright, so we have a horizontal shift. Is it right? Left. Okay, left 3, right? So 1, 2, 3. Okay. And then we have what? What's our other one?
Vertical shift up.
Alright, so up once. So that means that our starting point is here. Because I just took my dot. You know, we always start at the origin, right? Because our original graph looks like this, right? Well, that was really sloppy, but it looks like that. So our dot went left 3 and up 1. Agreed? Okay, great. So now that we have that, the question is, well, how do we find our second point? Well, you guys are more than welcome to use a T-chart. Okay, have at it. Good luck. Have fun. Or you can use my method. And my method is fairly simple. All we do is we take our dilation point, which is 2. Alright, so I was saying the dilation point, right? So I had it backwards. I am sorry. Okay. Yeah, because remember how I said over here with transformations that your A is considered your dilation point? So when you use this method, I hear a lot of people say it's a dilation point. It's the same thing as a vertical stretch or shrink. Okay?
So it's not, is it a reflection?
All of that deals with the same kind of concept.
Oh, yeah.
You're reading way too much into it. Okay? Alright, so I'm going to show you what the value is, and then I'll show you why this method works, okay? So let's just pick a point, because you guys are used to doing a T-chart, right? So let's pick a negative 2. If I was to plug in a negative 2 as my input value, so I want to know what's my output value there, what would we get?
Square?
Wow, you guys,
3.
thank you for doing the mental math. You guys were having me worried there. What's negative 2 plus 3?
1.
Oh, 1.
Wow, you guys, come on now. What's the square root of 1?
1.
What's 2 times 1? What's 2 plus 1? Whew, you guys are really worrying me. Come on, that's simple math there. Alright, so this output value is right here, right? Yes? Okay, and you could keep doing a T-chart and plugging in points and have at it. Now, I knew that one would come out nice and neat. Because I was using my method to where this dilation point right here that says 2, the vertical stretch, means that I'm going over 1 and up the 2. So you see how we went over 1 and up 2? See that? And that's because before, our parent function is like this. Because square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and so our parent function looks like this. And so what we're doing is we're taking the next value, which is here, and we're dilating it to this point. So the distance between these 2 points is no longer right 1 and up 1. It's right 1 and up 2 because you're vertically stretching it. You see that? That's kind of the process in behind it. Now, if you guys remember how to dilate, it makes perfect sense. For those of you who don't remember how to dilate from geometry, that's not going to make sense. Okay?
I'm confused.
Sure.
Right. Yeah.
Do you understand how I got this point here?
No, I don't get it.
You don't understand how to plug in an input value and get an output value?
Oh, so you got 3.
Do you understand how I plugged in -2 and got 3?
Yeah.
So do you understand how I got this value?
Yeah.
Okay. So now I'm explaining why my method of going right 1 and up 2 works.
Wait, where you get -2 from?
I didn't get -2. I said right 1 up 2.
No, I'm talking about in the radical.
Oh, I just picked a point.
Oh, you just picked a random?
Yeah, I picked a random point. I just picked -2. I knew that -2 would be a nice, neat number because I'm using the little cheat method, but, you know, it's your choice on there.
So right one always stays the same.
Yeah, right 1, and then you go up or down whatever your dilation point is. But do you guys know what dilation does? Like what it means?
It makes some bigger or smaller.
Do you guys understand this is a vertical stretch? So do you understand that we're making the distance between these points bigger? By 2? Do you guys understand that? So do you understand why it wouldn't be 1, 1, it would be 1, 2 now? Because you're stretching it vertically, right? Do you guys know what it means to stretch something?
Make it bigger.
Yeah. So when you are like stretching your body, you're trying to, push your limbs out as far as they can go, right? Yes? And when you're cold, you shrink down because, you're kind of huddled up in yourself trying to keep yourself warm, right? And you're shivering, right? So you're trying to keep all that body heat in. So 2 is a vertical stretch. So we're stretching it vertically, not horizontally. So instead of it being 1, 1, it's being 1, 2 because we're stretching that up distance by 2. Does that make better sense now?
Yeah, I got it. Two more questions.
Yeah, go ahead.
So what determines whether it goes up or down?
Then whether it's positive or negative.
Okay, and what's that little thing on the graph?
Which graph? This one was just a parent function.
Okay.
That was just a mark. All right. Let's see. If we're graphing this, it would look something like so. That would be what the graph looks like. I was showing you guys the parent function. This is what the square root of x looks like, right? But it shifted and had a vertical stretch.
It's really popular.
How about this one? Tell me what's going on.
Horizontal shift to the right.
To the right? You guys agree with them? What about vertical shift?
There's,
Why?
okay.
So I don't have to write anything down for the horizontal shift, right? So for the vertical shift. So I just leave it. And don't worry about it. No number? Don't worry about writing anything down for it.
Oh, we have to do that. Like, tell what we're doing and stuff.
Yeah, because I actually have you guys in the directions. I say describe the transformation, then graph. So I was trying to do it in my examples. All right, so this starting point is actually just right here. Really not all that bad, right? It's just... We do have a vertical shrink. This is shrinking. What else do we have going on? A reflection. So, I said that our parent function goes up like so, yes? If it was reflecting, then it goes like this.
Yeah.
So see how it looks like a sideways parabola? Sideways quadratic? That's what a reflection does. What does this mean for our problem? Oh, nothing. I still go right 1. But instead of going up 3/4, I need to go down 3/4. Well, Sykes, how do we do with 3/4? Well, I'll show you how to do 3/4. And let me zoom in for this so that you guys can see it. Can you guys see that a little bit bigger?
Wait, so you do what?
What do you mean you do what?
Right, you
you always go right 1, but instead of going up 3/4, we're going to go down 3/4.
Well, you always go right.
Yes, we always go right 1.
Even with the first one we did?
Yes, even with this one we did. We went right 1. So we always go right 1.
And then we go down.
Well, this time we're going down because it's a negative, right? So that reflection we have to take in consideration.
That's 3/4 right there.
Yeah, just put it in between because you guys are plotting on these tiny graphs, right? If it's a fraction, just put it in between. I'll get what you mean.
How did you go down 3?
Yeah, I don't understand how that's 3/4.
Okay, you guys understand?
Oh, 3/4 is 1. I forgot.
Yeah,
4/4
you guys,
is
3/4 is
Okay.
0.75, right?
Okay, yeah.
It's less than
I
1.
understand it.
You guys are really worrying me today. You guys are really worrying me. What about 1/2?
That's going to be at 1 hour.
Okay, that's less than 1, yes? What about 2/3?
That's still less than
3/7?
Less than 1.
4/7? 5/4?
more than 1.
More than 1. Okay, I was just making sure. So if it was 5/4, just put your dot here. Bigger than 1. There you go. Done. See? Don't make these overly complicated, please.
So it's a reflection, so we got to write 1 above it.
Huh?
Never mind.
It's a reflection because the graph is now decreasing. You see this?
Oh.
If it was a positive 3/4, the graph would look like this. Now, a couple of things when you're graphing these. Please don't draw them like this. What kind of graph did I just draw there? A linear. Actually becomes a ray because you don't put both arrows on them. Please try to curve them a little bit because what our square roots do is they kind of level off as you are square rooting it. Okay? So just be mindful of that. Any other questions?
Oh, that's it?
Oh, yeah. I told you this wasn't overly complicated. Well, let's do one more. All right. How did we find the first point?
We did horizontal shift left 4.
Okay. Horizontal shift left 4, and
And
then?
then down 1.
All right. So my vertex point is -4, -1, right?
Mm-hmm.
So if I didn't ask you to describe the transformation, you would just go to -4 and -1. Put your point. And you guys are using the transformations to find that.
Oh, you always go mark 0, 0.
I don't need to. That's where the parent function is, but we're not graphing that. All right, how do I find my second point?
Down 5. Or
So I just go down 5 like this? Okay, right 1, down 5.
Why you go right one in?
You always go right 1. Because we're always doing the next number in our T-chart. In this case, it would be -3.
and then draw your arrow.
Yep, so we draw it. So it turns out to be something like this. It's kind of a very steep.
So, I placed, what number did I placed -3 in there and got the same thing.
Yeah, that would work.
Oh, okay.
Now, it works on this because the 5 is a whole number. If it was a fraction, then you would get a decimal,
Okay.
right? Okay. All right, any other questions? Seem easy enough?